Good day, everyone. How we are doing? I believe we're great. So, without wasting much time, in our previous video, we discussed the theory of electrolysis. We've discussed the mechanism, we've discussed examples of electrolysis, and so on. In this video, we'll be looking briefly at Faraday's laws of electrolysis. Michael Faraday gave two laws for electrolysis that are very important when it comes to the subject of electrolysis. So I will start with the first law. Faraday's first law of electrolysis, if you want to write it down, you can write it down. Faraday's first law of electrolysis states that the mass of an element deposited during an electrolysis is directly proportional to the quantity of electricity passing through the electrolyte. So, by that, mathematically, so we're talking about the first law. First law. So, mathematically, Faraday is telling us that what determines the mass that will be deposited for any element during electrolysis, the mass of the element deposited will be directly proportional to the quantity of electricity being supplied. So M represents the mass of the element deposited, Q represents the quantity of electricity that is passing through the electrolyte from the external circuit. So, but then we all know that current in science is defined as the rate of flow of electricity, which is the quantity of electricity divided by time. So if you should cross multiply from here, we could clearly see that the quantity of electricity is the product of current and time. So this is one formula you should take note of. Let me call this 1.0. So I would call this 1.1. So if you should substitute 1.1 into 1.0, we can then say that the mass is directly proportional to the product of current and time. If we get rid of this proportional sign, M becomes equal to, you introduce your constant. The constant in this case is Z. Some textbooks use E. Regardless, just know what it stands for. That's the most important thing. So I have this to be 1.2. So this is what we have, where this quantity here is a constant. Take note of that. So these are the relevant equations that can be gotten from the first law of what? Of electrolysis. They're going to come in handy. Now let's talk about the second law of electrolysis quickly. Second law. Second law. Faraday's second law of electrolysis. Faraday's second law of electrolysis states that when the same quantity of electricity is passed through two different electrolytes, the mass of each element that would be deposited is inversely proportional to the charges on the ions of these elements. For this law to make sense to us, let's consider an electrolytic cell, two electrolytic cells. Let's say on one we are discharging, say, aluminium. On another electrolytic cell, we are discharging, let's say, magnesium. Just follow through with the explanation. Now, if I should supply the same quantity of electricity to these two electrolytes. So remember, electricity is the movement of electrons. So for understanding's sake, I would say, for instance, let's say we supply these two sets up with 6 moles of electrons each. So if we supply 6 moles of electron each to these different elements, the same quantity of electricity is being supplied to what? Two different electrolytes. Okay. Now, for 1 mole of aluminium, the oxidation state is 3 plus. This is 2 plus. So to deposit 1 mole of aluminium, you need 3 electrons to be given to this aluminum. So it therefore means that these 6 moles of electron would be accepted by 2 moles of what? Of aluminum ion. So we're trying to say 2 moles of aluminum ion would actually accept these 6 moles of electron to become deposited as 2 atoms of aluminum. But let's look at this case now. In the case of magnesium, the charge of magnesium is plus 2. The charge of magnesium ion is plus 2. So this ion needs just 2 electrons to become discharged. And then we are supplying a total of 6 electrons. It can be pretty clear that in this case, we would need a total of what? 3 magnesium ions now to successfully accept these 6 moles of electron to become deposited as 3 magnesium atoms. Now, what do you notice about this now? It means that the higher the number of charge here, the higher the charge on top of the ion, the lower the mole that is being discharged. The lower the charge on top of this ion, the higher the mole that is being discharged. Hence, Faraday's second law states that if the same quantity of electricity is passed through different electrolytes, the relative number of moles of the elements that would be discharged would be inversely proportional to the magnitude of the charge that they carry. So it means the higher the charge, the lower the magnitude, the number of moles that would be discharged. This is the statement of the second law. So basically, the second law is telling us that what? The amount, which is the mole that would be discharged when the same quantity of electricity is passed through different electrolytes, is what now? It's actually inversely proportional to the charge of the ions. So this is what we have. Now, if this is what we have, we can actually change this to equal to, so we have N is equal to K over your Q. All right. So if you cross multiply, you are going to have NQ is equal to K. Now, if the product of N and Q is a constant, we can say N1 Q1 is equal to N2 Q2. So this formula can come pretty handy. So if you have a question where they say the same quantity of electricity is passed through different electrolytes, you should know that question is a statement of the second law. You should take note of that. So this is what we have for the second law. N here represents the number of moles, or it can also, remember, mole is equal to mass over molar mass. So it means number of moles is also proportional to mass. So you could also use it as mass. You get, so here can be M1 Q1 is equal to M2 Q2. This would come in handy. Now, let's derive some mathematical expressions from these two laws now. Okay, I would continue from here. Please, I want us to pay rapt attention. Now, remember that the Z here is a constant. Okay, Z is a constant and IT. So this implies that if we combine, so by combining law 1 and 2, remember I said this can also be mass, take note of that. So I can say the mass is inversely proportional to the magnitude of the charge. So if we are to combine law 1 and 2, what are we going to have? We're going to have that what from the first law, mass, right, is directly proportional to the quantity of electricity being supplied. Okay. Then from the second law, it's inversely proportional to what? The charge of the ions. Now remember, the charge that the ion carries is what determines what the number of electrons that would be accepted or given off. That should be established. Now, and this charge, if in this case we can see this is taking 6 electrons, 6 moles of electron. So in this topic, 6 moles of electron is equivalent to 6 Faradays of electricity. Take note of that. So if I write 6 moles of electron, it's equivalent to me saying 6 Faradays, or you can simply say farads of electricity. All right. So it means, and 1 Faraday of electricity, 1 Faraday of electricity is equivalent to 96,500 coulomb. That's for 1 Faraday of electricity. So if for 1 mole of aluminium, 1 mole of aluminium, we need 3 Faradays of electricity. So 3 Faradays of electricity now would correspond to what now? 3 times the value for 1 farad. Okay, so it means this denominator here, I can write that as what? The quantity of charge. The quantity of charge from this. This is the charge on the electron, remember. So if this is what we have, we can simply say that M, in this case, which is the mass, is actually equal to, we introduce our constants, remember? So we have constant times your Q, then divided by the quantity of the charge, the total quantity of charge, remember, will be gotten by what? Multiplying the charge here, which is 3 in the case of 1 mole of aluminum. If you multiply 3 with 96,500, you are going to have your quantity of charge that is needed. Quantity of charge per mole. Meaning quantity of charge that is needed to do what? To discharge 1 mole of that particular element. So I have K times Q. To get this denominator, it's going to be the value for 1 farad times what now? Times the charge that you have on top here, which is small letter q, according to the second law here. So this is what we have. Now we're going to add something to this now. For a particular element, the quantity that is constant for a particular element is actually the relative molecular mass. We have the what? The relative molecular mass. You give me just a minute. Let's take off this part of the board. All right, now we've cleared this part of the board. So from here now, what can we do? So we said this constant here can be taken to be the relative molecular mass of that element or the atomic mass of the element, because that is a constant for every element under discussion. So I'll come down and say, but my K there can be taken to be the relative molecular mass of the element or the atomic mass as the case may be. So therefore, our mass would be equal to, this now changes to relative molecular mass or the atomic mass times the quantity of electricity supplied, all divided by our constant, which is 1 Faraday, times what? The charge of your ion. So this formula would come pretty handy. All right. So I'm going to call this 1.3 from the board. So if this is what we have, some questions, some calculations you would see in your exam will be centered around volume. All right. So if our question is centered around volume, what are we going to have? We can say, but for those that have watched my video on mass volume relationship, I have established that what? Mass over, okay. Before this, let me do this. This equation can be rearranged to be mass over relative molecular mass, right? Equal to Q over 1 farad times the charge of your element. If you should cross multiply, it's the same thing. So nothing was changed essentially. So I'll come down and say recall. For those that have watched my videos on relative molecular, on mass volume relationship rather, we have established that what mole is equal to mass over molar mass, which is also your relative molecular mass, and it's also equal to volume over molar volume. And molar volume is 22.4 dm cube. So if this is true, it means this is mass over molar mass now, mass over relative molecular mass. We could replace this part of this formula with volume over 22.4 dm cube equal to Q over 1 farad times Q. I believe this is clear. So if we make volume the subject of formula, we can say volume would be equal to 22.4 dm cube times Q, all divided by 1 farad times Q. So let's call this 1.4. So this is a formula you use whenever a question should, if the question should ask you to calculate the volume, especially the volume of oxygen. When they ask you such question, you simply plug in this. This is a constant, just in case the molar volume, if the options are given in centimeter cube, ensure that you use 22,400 centimeter cube in place of this. Why? Because, note, 22.4 dm cube is the same thing as 22,400 centimeter cube. So depending on what is in the options, you choose which to apply in your formula. Q represents the quantity of electricity that's being supplied from the external circuit. 1 farad is equivalent to 96,500 coulomb. Then your Q here represents the charge that the elements carry, the ion of the element. What is the charge? That's what you have here. So with all this now, we can now go into our calculations in our JAMB and WAEC. Let's get right into it now. All right, now let's look at this first example together, which says calculate the mass of silver deposited when a current of 2.6 ampere is passed through a solution of silver salt for 70 minutes. We are given the relative molecular mass of silver to be this, and then 1 farad, of course, is 96,500 coulomb. When you see a question like this in your WAEC or your JAMB, what you simply do is to use your formulas that I've derived. There is another method you could use called the direct proportion method, which I teach my students in class. But to save our time, we'll just be working with the formula method. If you still want me to teach you the other method, you can drop your comments in the comment section. Now, working with the formula method, we are looking for mass. So I state the formula for mass. We know that the mass will be equal to what? We just derived the formula. So the mass will be equal to your quantity of electricity, remember, would be multiplying what? Yes, I want you to guess. So your quantity of electricity, you used it to actually multiply your relative molecular mass in your formula, relative molecular mass times Q, okay? Then you divide with the value for 1 farad multiplied by small letter q. So this is the formula we have derived. So we bring out our parameters where your relative molecular mass was given in the question to be what? 108. So you simply say 108 grams. Your Q, we've derived the formula for Q before now, where we say Q is equal to current times time. And in the question, the current was given to be 2.6 ampere. So my Q becomes 2.6 times, my time is 70 minutes. Always convert your time from minutes to second. So you multiply that 70 by 60 to make that conversion possible. So the unit for coulomb, for quantity of electricity is coulomb. All right, in this case, coulomb. So you punch your calculator and then you have your answer. So we have 2.6 multiplying 70 times 60. So that gives me the value of 10920 coulomb. Yes. What parameter do we need again? Q. 1 farad, of course. You know 1 farad is equivalent to 96,500 coulomb. And then your Q would be equal to, we're talking about which element in the question? Silver. So in case you don't know, the charge of silver has a charge of +1. +1. Take note of that. So you're working with the magnitude here, which is 1. So your Q here is 1. So that's how you get your Q. Q is just the absolute value of the oxidation number of the element. So if you plug in all of these into your formula without wasting any atom of your time, you get your answer. So your relative molecular mass for silver is 108. So you say 108 times your Q you've calculated to be 10920, then divided by the value for 1 farad is 96,500 times the charge of silver is 1. So this would carry grams. So let's punch all of that in our calculator. We have 108 times 10920 divided by 96,500. And that gives us a value of 12.22 grams. And that becomes your answer. So when they give you any question like this formula would give you the result without wasting your time. So this gives us the solution to this problem. We move to the next question. Okay, now let's look at the second example on the board, which says, what volume of oxygen measured at STP would be liberated on electrolysis by 9,650 coulombs of what? Electricity. Okay, now oxygen is only liberated in electrolysis whenever hydroxide ion from the solvent is what? Is being discharged, from what we learned. And from what we learned in the previous video, when that happens, the equation at the anode will be 4OH minus, okay, give us 2H2O plus O2, yes, then plus 4 electrons. So this was the equation that we got in our previous class. So why did I need to write the equation in this case? Essentially to let you know that the total charge contribution here, I know most of you would say your Q in this case is going to be 1, but please, the total charge contribution in this case is actually 4 times 1. So you're multiplying this with 4. So your Q is actually 4. Another way you can look at it, remember I said Q represents what? The charge, 1 mole of the substance, okay, being discharged. But then, remember that also corresponds to what? The number of electrons that is involved in the discharge of 1 mole of that substance. So from this equation, for 1 mole of oxygen to be discharged, we can see now that what? The hydroxide ions needed to lose a total of what? 4 electrons. Now, another way you can look at it without even writing this equation is just to know that oxygen is a diatomic molecule. And then for 1 mole of oxygen, when you ionize oxygen, the charge of oxygen is -2. So since oxygen is diatomic, it means the total charge contribution in this oxygen now will be 2 times 2, which is also what? 4. So it means you can get this 4 even without writing this equation. Just understand that your Q, your small letter q in your formula, represents what now? The number of electrons that is involved in the discharge of 1 mole of that substance. So the number of electrons involved in the discharge of 1 mole of oxygen is 4 electrons. So we can now go straight to write our formula. The formula says what volume of oxygen. So we use the formula derived for volume, which says that what volume is equal to 22.4 dm cube, which is our molar volume, times what? Times Q, divided by what? Now, it should be noted that, please, it's not compulsory for you to write this. For your JAMB exam, you don't have the luxury of time to be writing a lot of all this. So just know that for oxygen to be discharged, you need just 4 electrons. I don't know why I'm emphasizing this. Please jot that down. Now, that said, the denominator of our formula is what? It's actually what we have here is 1 farad, which is our constant, then multiplied by Q. So if we should substitute, our answer simply becomes what now? 22.4 times the quantity of electricity that is being supplied, according to the question, is what? 9,650. So 9,650 divided by 1 farad as usual is what? 96,500. So 96,500, then times the quantity of electricity involved in this process is what? 4 moles of electron, which is 4 farads. So your Q here is 4 dmq. So you punch your calculator and you have your final answer. So I'll punch that now. 22.4 times 9650 divided by 96,500 times 4. So that gives us 0.56 dm cube. So this is the answer to this problem. We move on to example 3. All right, now let's look at our third example. It says if 10.8 grams of silver is deposited in a silver coulometer connected in series with a copper coulometer, the volume of oxygen liberated is dash. So how do we deal with this? First of all, you should understand that this question is talking about 2 different electrolytic setups that is being connected with a single wire in series. So the message being passed that is what? The quantity of charges released in the silver setup would be equal to the quantity of charges that would be entering the copper setup. You are not making use of the copper for anything in this calculation. You're not making use of it at all, because what was given to you is what? The mass of what? Silver. I know you're wondering, then where is oxygen coming from? They said the volume of oxygen liberated is what? Remember, most electrolysis occur in aqueous media. So they're trying to say oxygen is being liberated at what? At the anode. So we're calculating the volume of oxygen being liberated at the what? At the anode. Remember, the quantity of electricity that will be liberating the oxygen at the anode will be the same quantity of electricity that will be liberating what? Silver at the cathode. So the quantity of electricity that applies to silver is the same quantity of electricity that applies to the deposition of oxygen. So the first aim is for you to calculate the quantity of electricity that actually did what? Liberated this 10.8 grams of what? Of silver. So how do we do that? We make use of our formula that says what? Mass is equal to relative molecular mass, right? Times what? Your quantity of electricity, all divided by the value for 1 farad times your Q. So for your silver, which is Ag plus, remember the charge there is 1. So if we are to write the equation for the deposition of silver, remember it's going to be Ag plus 1 electron to deposit Ag. So for 1 mole of Ag to be deposited, we need just 1 farad of electricity. So that's Q, represent this 1. So if we are to substitute, we are going to have that what? Our mass of silver deposited is 10.8. So we say 10.8 would be equal to your relative molecular mass of silver was given to be 108. So we'll say 108 times the quantity of electricity supplied is what I want to know. Then divided by your value for what? For 1 farad. So we have 1 farad times your Q. In this case, for silver, Q is 1, which is 1 mole of electron. So from here, what are we going to have? We're going to have that 1 times 1 is 1. So at the end of the day, Q would simply be, this is 10.8 divided by, denominator is 1, so we can just say 108 Q. We divide both sides, Q is going to be what? 10.8 now divided by 108. So that's your quantity. So Q would be equal to, take note, if you'd like, if you so much like, you can actually convert this to 96,500, but I feel you will still have same answer. Let's see how it goes. So you have 10.8 divided by 108. So that gives me 0.1 farad. In this case, this is farad. Okay, so if you should punch that, we have 0.1 farad. Now we can now go forward to calculate the volume for oxygen now. So I'll come down and say, for oxygen, remember oxygen is diatomic molecule, which is 2O2 minus. So the total charge is 4, like I said in the previous example. So the formula we use to calculate the volume of oxygen will say what? Volume is equal to what? 22.4 dm cube times your charge, which is Q, divided by the value for 1 farad times your charge. So our answer is going to be what? 22.4 multiplying our Q, remember now, is this 0.1 farad. 0.1, then divided by this farad, divided by 1 farad. So you can see this farad would cancel this farad at the end of the day. Then your Q for oxygen is actually 4. 2 times 2, remember, 4. Then your unit will be dm². So when you punch that in your calculator, you have 22.4 times 0.1, then divided by 4, you'll get 0.56 dm³. So that gives you the answer for this problem. Like I said, you could still use 96,500 in place of this 1F. You would still arrive at the same answer. So this gives us the solution for this problem. Let's go to example 4. All right, now let's look at this fourth example. It said the same current is passed for the same time. The same current is passed for the same time. This is already a statement of the second law of what? Electrolysis. Okay, because we have same current and same time, it means our quantity of electricity is equal, which is current times time. So if the same current is passed for the same time through solutions of this and this connected in series, how much silver will be deposited if 1.0 grams of copper is deposited? Whenever you see electrolysis questions like this that relates the amount of two different elements, we are going to derive a formula that can help you in your exam for that. Remember that generally, we have already said that what? That M would be equal to your relative molecular mass, okay, times your quantity of charge divided by 1 farad, then times what now? Times your charge. This is what we have already said. Now, they say that the quantity of electricity in both cases, they are the same. The same current is passed at the same time. So it means in this case now, in my derivation, this Q is constant. Of course, 1 farad is a constant. So this is a constant, this is a constant. For the two elements we are considering, the value of Q will vary. For the two elements we are considering, the relative molecular mass will vary. Now, I can now say that the mass that is being deposited, I can say that M would be what? Directly proportional to your relative molecular mass. Let me represent it as capital letter M, okay, divided by and inversely proportional to what? To Q. I can make this statement. I'm deriving a formula. So from this, we can say M is equal to Km over Q. So if I should cross multiply, I'm going to have that MQ would be equal to Km. And if I should divide both sides, we can say MQ over M. This small letter m, please, let's differentiate them, over M, capital letter M, equal to our constant. So if this is constant, we can now state a formula that says, therefore, M1 times Q1 all divided by capital letter M1 will be equal to M2 Q2 all divided by capital letter M2. So this formula can come in handy. So I would say you should write this formula in your formula book, take note of it. So we can make use of this formula to answer this particular question now. So take note, M1 represents the mass of the element, the first element discharged. Q1 represents the electrons involved for that first element. Capital letter M here represents the relative molecular mass, respectively. So now we are looking for, they said, if 1.0 gram of copper is deposited, we should find how much copper is being deposited. So let's say we're looking for M2. This is the mass, let's say this mass of copper being deposited. Where, let's bring out our parameters. M1 represents, let's say 1 is standing for the mass that was given in the question, 1.0 gram of copper. So this represents, 1 represents copper. So the mass of copper in the question is 1.0 grams. Okay, what else? Q1. For copper to be deposited, you need 2 moles of electron. Remember, copper is Cu2 plus, while silver is Ag plus. Have this at the back of your mind. So for copper, your Q will be 2. The relative molecular mass of copper is 64, given here. Now, your Q2, which is coming to silver now, Q2 will be, the charge of silver is 1, as we can see. Then what else do we need? M2. The relative molecular mass of silver is 108. So if you plug in all of this and then you make M2 the subject of formula, M2 would be equal to, if you cross multiply, this will multiply this, so you have M1, Q1, M2, then divided by, if this should multiply this, since you are making M2 alone, you have to divide both sides with the coefficient, which is Q2 and M1. So if you divide both sides by Q2 and M1, you have M1, then Q2. So you plug in this, and then you have your final answer. So your M1 is what? 1.0 times your Q1 is 1 times your M2, capital letter M2 is 108, then divided by your M1, capital letter M is 64, then times your Q2, where are you? Your Q2, sorry, Q1 is 2 over here. That's a mix up. Q1 is 2. Q1 is 2. Then Q2 is 1. So Q2 is 1. Then you put your grams, the unit at the back. So you punch that in your calculator and you have your final answer. So let's punch that quickly. You have 2 times 108, then divided by 64. So that gives you 3, that's 3.375 grams. So that becomes your answer for this particular problem. So subsequently, whenever you see nature of problems like this, you don't need to start this up from the beginning. You just need to use this formula straight up. After you writing your formula, you cross multiply, you make whatever you want to make the subject of formula. We go to example 5 now. All right. Now, let's look at example 5. What is the quantity of electricity used when a current of 0.5 ampere is passed for 5 hours, 45 minutes? So this question is not asking us for amount, not asking us for mass, not asking us for volume. So we're not making use of those formula. Rather, they're asking us for what? Quantity of electricity, which is capital letter Q. So for me to calculate quantity of electricity, the formula is current times time. So in this case, the question gave us the current to be 0.5 ampere, and then the time was given to be 5 hours, 45 minutes. So you convert to seconds. We don't work with hours or minutes. So 5 hours is equivalent to, anytime you see hours, multiply with 60 times 60. Okay? Then whenever you see minutes, so I'm adding it, I'm adding this part to this part. Anytime you see minutes, you multiply by just 60. So when you do all of this, you have your results in seconds. So I'll punch that quickly. So we have 5 times 3,600 would give us 18,000. So we have 18,000 plus 45 times 60. We have 2,700 seconds. So by the time you add those, 2,700 plus 18,000, that would give me 20,700 seconds. So we can now calculate our value for Q and say Q becomes what now? My current, which is 0.5, multiplied by my time, which is 20,700 coulomb. So let's punch that. That's times 0.5. That gives me 10,350 coulomb. So you stop here, but if it were to be an objective question, if you would stop here, it's determined by the unit in which your options are expressed. So if the options are expressed in farad, sometimes the options can be expressed in farad. To convert coulomb to farad, you simply divide this, your answer, with what? 96,500. So you can also say this is the same thing as 10,350 divided by 96,500 farads. So that gives you the answer in farads. That's 10,350 divided by 96,500. So that gives us 0.1 farads. So that brings us to the end of this particular question. We still look at 2 more questions and we'll call it a day. Okay. Now let's look at the 6th example now. It said, if a current of 1.5 ampere is passed for 4.0 hours through a molten tin salt and 13.3 grams of tin is deposited, what is the oxidation state of the metal? So we're given the mass of tin deposited, so we can make use of our general formula that says what? Mass is equal to your relative molecular mass, right? Times your quantity of charge divided by the value for 1 farad, then multiplying value for 1 farad multiplying Q. So straight away we're going to substitute straight into our formula. We were given the mass deposited to be 13.3. So 13.3 is equal to, the molecular mass of tin was given to be 118.7 times. Remember, Q is equal to current times time. This should be at the back of your mind. So the current given in the question is, I think, 1.5 over here, 1.5 ampere. So we substitute 1.5 times our time. The time is 4 hours, but we don't work with hours, remember? So I will say times 4 times 60 times 60. Remember, whenever we have hour, we multiply by 3,600, which is 60 times 60, to convert to seconds. So all divided by the value for 1 farad would be what? 96,500, then times 14. Now we are looking for Q. Q represents, remember, the absolute value of what? The oxidation number. So indirectly, this question is asking us to look for Q. That is what it means. So if we are to break this down further, we're going to have 13.3 would be equal to, now you punch your calculator, 118.7 times 1.5 times 4 times 60 times 60. So that's giving me 2563920, all divided by 96,500 cubed. So at the end of the day, without wasting much of our time, if you should cross multiply and make Q the subject of formula, Q would be equal to, this is over 1, so 1 times this will still give you that figure. So you have 2563920. If this should multiply, the coefficient of Q will be this number and then this number. So we're dividing with 13.3 times 96,500. So we punch that in our calculator. So 2563920 divided by 13.3 times 96,500. So that gives us 1.99. So obviously, approximately, our Q will be equal to what? 2. So it therefore means, therefore, the oxidation number of tin is plus 2. Since tin is a metal, which corresponds to option B here. So that's how you get your oxidation number. All right, we're going to draw the curtain close here. But before we all go, I would write out some questions for you all to solve, and then drop your answers in the comment section. All right, so here you have your exercises. Attempt them, drop your answers in the comment section for me to see. Thank you very much for sticking around. Please ensure you share this channel to your friend, like the videos, and also drop comments. God bless you. I'll see you in my next class.